So a bullet strikes a block that's at rest on a horizontal frictionless table. And you always want to make note of things that are in the problem, like frictionless. It means that the block is going to be allowed to slide across the table without slowing down. The surface of the table is a height h above the floor, the impact of the bullet, and the block slide off the table and hit the floor at distance x. So it's a projectile motion. A bullet striking a block, that's momentum. And as we find out later, there's going to be energy involved as well. So the first thing to do is figure out how fast the block is moving off the table. You can either use momentum or projectile motion to solve this, except for the projectile motion, you're going to be using the distance x, and that's not in our list of approved symbols. So projectile motion's out. You have to use momentum to figure out how fast it's going. Well, since it's frictionless, however fast it's going after the collision is how fast it will be going as it leaves the table. So momentum is the appropriate way to go here. The bullet has momentum mv naught to start with. Well, actually, probably a preferred start is some indication that you're using conservation of momentum. The bullet's momentum is v naught times m. The block doesn't have any momentum since it's initially at rest. Afterwards, those two masses have combined, m plus 100m, times their new speed. So this becomes mv naught equals 101m times v prime, so divide v naught over 101 equals your new speed. If you left the masses in there, okay. It won't be as clean in the end if you leave m in there as it will be if you eliminate variables. The more you can simplify something, especially algebraic problems, the better off you're going to be later on in the problem when you do substitutions. So now we have the new speed of the block as v naught over 101. What's the change in kinetic energy of the bullet block system during impact? First, ask yourself, will the energy change? Sometimes you get questions like this, what's the work or what's the energy, and it turns out to be zero, just by law or rule. So just make sure that it's going to change at first. It's an inelastic collision. Do we have energy change during inelastic collisions? Yes, we do. If it's an elastic collision, if the bullet had, say, bounced off of it, then we wouldn't have any energy change. So we just go ahead and write 0 without doing any work. But it's inelastic collision, so we have an energy change. So we need to find out what the change in energy of the bullet block system was. The bullet block system takes into account both the bullet and the block. Prior to the collision, the only thing that had kinetic energy was the bullet, because it was the only thing that was moving. Its kinetic energy is 1/2 mv naught squared. Straightforward. After the collision, now both objects are moving. 1/2 times the mass. Mass is now 101m times its new velocity, v naught over 101 quantity squared. Oops. Can't do that. 101m times v naught over 101 quantity squared. You could do this. That's the difference in kinetic energy. I'm going to go ahead and do the simplification just to see how it works out. 101m, that's v naught squared over 101 squared. So you end up with m v naught squared over 202. my algebra right there. Not the greatest answer ever, but it's slightly more attractive than that. No, it's not that actually. Oops. Minus mv naught squared over 2. Because we need to subtract this energy from our final energy. We simplify that. Multiply by 101 to find the common denominator. mv naught squared over 202 minus 101 mv naught squared over 202. So that results in minus 100 mv naught squared over 202. That's the difference in energy. I want to say there's some sort of algebra mistake in there, but I can't see it right away, so. Change is final kinetic minus initial kinetic. Final minus initial. Maybe something better, a better simplification than that. I don't know. That's one way to do it. That's why you end up. But like I said, this is perfectly acceptable. Just finding the difference between them is what they're asking. So how far off of the table does it go? Hopefully at this point you've recognized projectile motion. What's the most important thing in projectile motion? Time. How do we solve for time? H. We use the y direction to solve for time. Change in y is v naught t plus 1/2 at squared. Change in y is down h. Initial velocity in the y is nothing. 1/2 negative g times squared. Positive. So time is 2h over g square root. To find the distance, we use the x direction. Change in x is v naught t plus 1/2 at squared. In the x direction, there's no acceleration. So change in x is velocity here. V naught over 101. Times time. Square root 2h over g. And there's no simplifying that one. So now we've changed up the problem. Say the bullet passes through the block instead of remaining in it. Time to reach the floor from the edge of the table, greater or less or the same. If we look back, the time depends only on the height of the table and gravity, neither of which is affected by this change, so same. And you could write, that's a pretty good justification. V naught, no matter. Now the distance the block would go, greater or less to the same, we look at our equation for distance. That is affected by V naught. So according to our equation, V naught over 101 square root of 2h over g, if the thing goes through it, does V naught change? How does it change? Does it go faster? Slower. It goes slower. Why? Impulse is less. You could also argue that the bullet carries away some momentum, so it couldn't have transferred as much momentum to the block. It also carries away energy, which didn't go to the block. So since VO is smaller in the collision, change in x is going to be smaller as well, according to that. Bullet carried energy, some form of that.